Well, right now it's sitting at just 70 or 72 people out of, and it's 97 people in the class, so it's very close to 75%. It's right on the borderline, folks. What happened, huh? The reason people are clapping because you're coming into class is we're right on the borderline of a quiz. And I think you just brought it over to 75 people. Oh, now it's definitely enough.
Now we're too many.
All right. Now you have to all go home. Ah, the true student. All right. Let's talk a little bit about Lab 2. The first thing is, this always happens. If you don't do the lab before you assign it, there's always something wrong. And I thought this one was very straightforward, but there was something wrong with the write-up. And what's wrong is that ports B5, B6, and B7, as I know, are shared with the programmer. The problem is that the programmer does not go into high impedance state when it is not programming. It goes into kind of a medium impedance state, like a 10K or so output impedance. That means that the three resistors corresponding to the three resistance measurement channels never get disconnected completely, and so the resistance measuring isn't auto-selectable. And so the fix for this is you can do either one of two things. One is you can just pull the programmer plug off every time, but that's tedious. And so what I suggest, and the way I change the documentation in the lab, is to make this A 5, 6, and 7, and then it works. Pardon me? Without a problem. No problem. So, yes. Oh, don't worry about changing your homeworks. No. I mean, give the TAs a hint of it. They're smart enough. They'll figure that one out. So, but it's an extremely minor change in your code. And so I don't think it's any problem in modifying. How long did it take you to modify it, Pavel, in your code? Well, maybe 8 seconds, yeah. So, the documentation online has been already modified, but you won't see it unless you refresh the cached version of the page. So you might want to do that. The only difference is the B's have changed to A's. Yes?
So the documentation actually also says you should be able to measure frequency from 100 hertz to 10K, but in the
100K.
it said one. Okay, so that's wrong.
I think it says 100K in the lab write-up.
Now it says 1 hertz to 10K.
It says 1 hertz? I thought it was 100 hertz to 100 kilohertz.
To 10K, but you said 10 hertz to 100. These numbers are backwards.
I'll go look at it, but I believe what it says in the lab write-up is 100 hertz to 100 kHz. Is that not what it says? 10K? All right. Well, 10K is all right. You could do 100K, but you have to go down to 100 hertz. The reason to go to 100 hertz is at what frequency of square wave input will timer 1 overflow at full clock rate? What? Very good. 200 for about 4 milliseconds. Very close to 4 milliseconds, just slightly over. Very good. So it'll overflow at 244. So what you'll get is all your measurements above 244 hertz will be fine with a times 1 prescaler, And as you go down to 100 hertz, which is the bottom of the range, it'll read 63 kilohertz. Ah! What? Because because timer 1 is overflowing. And so you have to auto scale by changing the prescaler to be set to divide by 8 for low frequencies. Now, how many people are driving the keypad off of port D? That's one the TA. Okay. All right. Now, that means there's a problem here. And that means you can't debug using the UART because the UART is port D0 and D1. That means you're going to have to debug by writing messages to the LCD instead, which is probably the cleanest way. Pardon me? Off of port D at the same time?
Yeah, I didn't use as many ones on the keypad. I only used those.
Ah.
You don't need all the ones.
You're quite right. How clever. All right. I like it. The one problem you got to look out for is that if you execute UART, oh man, UART init, if you execute that and never do a printf, D0 and D1 will not be under the control of the general I/O port I/O pins. They are dedicated to the UART, and they will not work with the keypad. So if you just leave this in here because you cut and pasted code from Lab 1, it won't work. You have to comment this out and all references to the UART before you can use the UART lines D0 and D1 for the keypad.
And symptoms will be, or the leftmost columns will not work.
The symptoms will be, yes, either the leftmost columns, or if you transpose my diagram, the top or bottommost rows won't work. 2 of the rows or columns won't work and the other 2 will. And you'll say, that's funny. It must be a bad connection. And then you'll spend 4 hours, which is what Pavel did. You'll spend 4 hours debugging. I'm picking on TA, sorry. You'll spend 4 hours debugging when you could have just remembered to disable that. We all do this. We all spend hours and hours debugging the silliest bit combinations because there are so many ways to break this chip with software. Okay? Oh, printing floating point. I put the directions for include. There's a library you have to link in, which is not included by default. I put the instructions for linking it in Lab 1, so that it's in the procedure section of Lab 2. It's in the procedure section of Lab 2 where you can find it easily. There's one line you have to add to the linker options in order to print floating point. Otherwise, you have to do the floating point conversion yourself. Boring. Any questions about Lab 2? So let's talk about keypads. Oh, one other thing before I start talking about keypads. What I specified on the board is that you could hook up a trim pot for measuring voltage, Vin, to +5, and that will certainly work, particularly if you're on the +5 scale, if you're on the 5-volt full scale VREF. But what if VREF is 1.1 volts? Then 8/10 of this trim pot is out of range. because once you get above 1.1 volt on the trim pot, the A to D converter will just read saturated, full scale. So if you want to make this a little more elegant, you can jump this, instead of to 5, you can jump this to AREF. And then as you change AREF in software, the voltage on the pin output from the microcontroller will change, and you will always have 0 to full scale availability for testing the A to D converter. AREF is on a port pin in the middle of the board, right? Port E. It says AREF on port E on the STK500. Jumper. Oh yes, well yeah, I think I said that once, but I'll say it again. You must remove AREF. You have to unmount the AREF jumper, which is, if you orient the STK500 with the microcontroller at the bottom left corner, then the first jumper here is what? You have memorized them yet? You better. You better look at those every time you pick a board out. That's V target. That's VCC. So this is VTG. The next jumper is AREF. The next jumper is reset. Then clock. They all have to be there. Except in this case, you're going to unmount AREF. You have to unmount AREF. Otherwise, you'll say, that's funny, my auto scale doesn't work. Okay, now to keypad. It is not exactly 1.1 volts.
So, how are we supposed to, do we need to pre-calibrate this? Like, we know that it's going to be 1.14 or something?
So there's no way to get around that except to put a digital voltmeter onto the pin and measure AREF and then type that into your code. That's correct. So you're going to have to measure 3 different values of AREF. Right, you have to measure the 5 volt value, which isn't exactly 5 volts, it may be 4.97. You have to measure the 2.56 voltage, which could be 2.56 volts plus or minus 10%. Since your voltage has to be accurate within 2%, you have to measure that. On every board, it's different. And you probably also better measure the 1.1. The band gap reference at 1.1 is more accurate, but it's still not, I don't think, within 1%. Does anybody know if it's within 1%? You had a question, sir?
So could you possibly use like voltage dividers and known 5 volts on the STK500 into the other ports in the array to auto-calibrate at the startup?
Oh, could you? So could you use? Yeah, I like it. So you could use voltage dividers off of the 5 volts into separate port pins. Let's say A2, A3, and A4. So you'd have known precision voltages into those ports, and then you could absolutely do a 2-point calibration. The way you do a 2-point calibration is V versus number. You set the multiplexer to ground, which is 11111, I think. You set the multiplexer to ground, and you get a reading. Then you set the multiplexer to A2 or whatever your standard voltage is. You get a reading. You draw a line between them, and now you know within a fraction of a percent what numerical values correspond to what actual voltages. That's a very safe way of doing it. Systematic way of doing it. which is also independent of the board, which is nice. Independent of the SCK 500.
Demo on our own board. Like, do you have
Yeah, you can demo on your own board. You mean the one you built?
Yes.
Sure, absolutely. If you want demo on your target board, absolutely. Just schlep it on over. Okay, now keypads. So the keypads are arranged. We have these 16 keypads. 1, 2, 3, 4, 5, 6, 7, 8, 9. Star, 0, pound, A, B, C, D, or some layout like that. They vary a little bit, but most of them are in that outline. And the way these are wired is as a 4x4 grid of wires. And at every point in the grid is a potential connection determined by the state of a push button. So every one of these grid points has a push button. And the way we're going to hook it up is we're going to hook the columns up to some port, x.0, x.1, x.2, x.3. So the first 4 bits of the port are going to be hooked up left to right. And then x.4, x.5, x.6, and x.7 will be used to hook up the rows. So any button connects one vertical wire with one horizontal wire. Now I've bought keypads at 3 different times, and every one of them has a different pinout. So there are 3 kinds of pinouts. There are pinouts at the top, 8 pins. Pinouts at the top, 9 pins. And pinouts at the bottom, 8 pins. The 9th pin changes state if any button is closed. Oh, what would you use that for? Interrupt. Keypad interrupt. But I'm only going to draw the 8 connections here because that's common with all the keypads we have. So, what we would really like, we have this rather abstract I/O device here. What we would really like is at the top level, we would like to have some string 31415 enter produced by the human by typing on the keypad, and we would like that string then to be this string without the enter, with the enter chopped off, to be available for some other task or process or function to use. So there are several steps we have to do to get from raw key presses to decoded string. The first is that we have to scan the buttons. We have to do this fast enough so that we're not going to miss a key down by a human. So about every 30 milliseconds or so, you have to test all of the buttons and see if any one of them is pushed. And of course, we have to debounce, because nobody wants to have 333114444 and so on in the number that comes out. So you have to debounce. That's actually more important for Lab 3 than Lab 2, but it is important for Lab 2. And then we have to form a string which might be ASCII, in which case we're going to have to do some manipulation of the button numbers to turn it into the ASCII codes, or it might not be. Or we might just go directly to an int instead of making a string. There might be some way of quickly going to an int. So we've already talked about button bouncing, so I'm not going to talk much about why we have to debounce, but I'll show you a state machine that does all this stuff. But we'll have to build up to it a little bit. The first thing we need is a button scanner, and there's a really clever button scanner that I read in a book by Peatman called Microcontroller Interfaces that does the entire keypad scan in 2-port reads. So, let me say it first, and then I'll write it out, and then I'll write it again. We're going to set 4 of the lines to output low. And then we're going to read the input on the other 4 lines with the pull-ups turned on. So if the button is not pushed, the inputs are going to be high. If a button is pushed, it will be low on the line. Alright, so we're going to set these low, read these with the pull-ups turned on. One cycle later, one machine cycle later, we're going to set these to outputs low, set these to inputs high, and read it again. If one button is pushed, then the top 4 bits will have exactly 1 0, and the bottom 4 bits will have exactly 1 0 when you read this. Alright, so that's the warm-up. Now let's write it out. So we're going to set, step 1 is set x dot 0 through x dot 3 to output and low. So we're going to set it to output and low. We're going to set x dot 4 through x dot 7 to input with pull-up. And then we're going to read the upper 4 bits. And since that's half a byte, we call that a nibble. So we're going to read the upper nibble. And then we're going to reverse this. We're going to set x dot 0 through x dot 3 to be inputs with pull-ups on. We're going to set x dot 4 through x dot 7 to be outputs and low. And we're going to read lower nibble. Then we're going to OR the nibbles together. And do a table lookup. For using this particular keypad in this situation, 1 button down is a valid button push. 2 buttons down is ambiguous and should be an error. Alright? 0 buttons down is, of course, valid. So, if exactly 1 button is down and one of these, and these are all low, then only exactly 1 of these lines can be low for 1 button down. Let's say this button has been pushed. Now we flip this around, make these outputs these inputs, and now we have a 1 0 1 1 here. And by reading the 0 on this line and the 0 on the previous cycle on this line, we know that that button is pushed. Furthermore, We know that no other button was pushed by accident during the time if there is exactly 1 0 in each of the nibbles. Okay? So we build a table with 16 entries. 1 1 1 0 1 1 1 0 1 1 1 0 1 1 1 1 0 1 and so on. All possible combinations of numbers that have exactly 1 0 in the low 4 bits and 1 0 in the top 4 bits. We take the scan code. These 8 bits are going to make a scan code, or the nibbles into a scan code. Then we're going to go through a table of 16 entries and find out which of the 16 entries, if any, are matched by the scan code. If none of them are matched, it's an invalid press. So the question is, if you had multiple button pushes, could you actually detect them and discriminate them? And the answer is sometimes. It depends on whether they're in the same row or not, the same column. But yes, you can make a shift key. You can make a shift key to double the number of functions, go to 32 buttons. For lab 1, you need what? 4 buttons? Lab 2, I'm sorry, lab 2, you need what? 4 buttons? Something like that? So 1 column is really enough. For lab 3, you'll need to enter numbers, so you'll need all 10 of these plus an enter key which you have to define, or more generally a terminator key that says the slow boring human is done. So maybe the star or whatever you feel like. Doesn't matter. So there's a test program. Yeah.
So we're scanning, this is going to have to interrupt every
Yeah, some scheduled task at least every 30 milliseconds or so.
Are we going to eventually get into using the actual interrupts from keyboard interrupts? Can we use that? Implement that here?
You could implement that here. You could do a if any bit changes on a port, on any port you can detect it as an interrupt. Every single pin on the CPU is a potential interrupt source. There's not only interrupt 0 and interrupt 1, but there's an interrupt on every single pin. So yes, you could do you. There is no lab that requires you to use interrupts on inputs as long as your code for reading the button is not blocking. You can't spin waiting for the key. You just have to check it, and if it's not valid, fall through and do something else. And that may be faster than an interrupt in any case for these simple keypads. Yeah, it eats about 10 microseconds. So it's not a huge kill, but yes, it might be nice to interrupt drive it. So the test code, which I suggest it's used really mostly to make sure your connections are correct for the keypad, is written as a program, but you will clearly have to convert this to a function that you're going to call over and over again in some state machine to figure out what's happening on the keypad. And So we're gonna start. I'm gonna not bother with some of the definitions and so on, but we're gonna do an unsigned car table, key table, with 16 entries. And I'm not going to enumerate all those, but they're going to be of the form 0xEE, 0xEB, 0xE7, and so on, blah, 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 down to 0x77, being all possible combinations of 2 hexadecimal digits with 1 0 in them, in each digit. Then we're going to drop into main, and what I did for the test program was just to bounce the button numbers out onto port B so that they could be displayed on the LEDs. So we're going to set DDRB equal to 0xFF to turn it on as outputs, and then we're going to set port B to 0xFF to turn off the LEDs. Now we drop into the usual forever loop. And what we're going to do here is we're going to set DDRD to 0x0F. So the bottom 4 bits are outputs and the top 4 bits are inputs. We're going to set port D to be 0xF0. Setting the top nibble to F means that the inputs have their pull-ups turned on. So this sets the ports to inputs. This turns on the pull-up resistors. This sets the port F here, sets the port to an output and pulls it low. Now we're going to do a delay underscore microseconds 5, and I'll tell you why in just a minute. It turns out to be important. And then do a key, this is going to be the key code, is equal to pin D. The first time I wrote this code was at home using a byte accurate cycle simulator, cycle accurate simulator. And I wrote the code without the delay, and it worked beautifully. So on Monday I came into the lab and put it on the microcontroller, and it totally did not work. So the simulator always lies. You should always remember that. That's first rule. You write it on your forehead. Simulator is always wrong. And the reason it's wrong is that it doesn't take into account a very subtle time delay that happens because of an electrical effect. And the electrical effect is caused by a capacitor I didn't expect. So pin looks like this. This is the output pin. There's the pull-up resistor. There's the pull-up resistor switch. There's a Schmitt trigger here, which is the input driver. There's a tri-state, which is the output driver. And then there's the piece you didn't actually build, but which is always there because wires are wires. and that is the parasitic capacitance of the port. And in the case of a 18-inch long cable hooked to the port, from the port to the keypad, plus the capacitance in the whiteboard, which is on the order of 20 picofarads between columns of the whiteboard, this is going to be greater than 20 picofarads. Parasitic capacitance. You didn't put it on there, it's just there. So, if the tri-state were turned on, if you were driving this as an output, let's say that you turn on the output high, you let it come to equilibrium, and then you suddenly switch the output low. What's the time constant for switching from one state to the other? (20 times 10 to the minus 12 farads times the Thevenin output impedance is 40. Actually, it's in the low state, 40 ohms. We'll call it 50 ohms. So that looks like about 100 times 10 to the minus 12. So that's about 10 to the minus 10 seconds. Bigger or less than a cycle? What's the cycle time on this machine? 60 nanoseconds, right? 16 megahertz, 60 nanoseconds. This is like 1,000th of a cycle. So it comes to equilibrium essentially instantaneously. But wait. Let's say that you're not driving the output high or low by means of this tri-state. Let's say the tri-state is turned off and you're driving it high through a 10 to the 5th ohm resistor. Because what's happening in this code is, now let's do this as a function of time and voltage on the pin. We start with it held in the output low state, and of course it's low, it's strongly low. We switch the direction of the port. The output stays low because it's now an input until we turn on the pull-up resistor one cycle later, at which time it starts to charge towards VCC through the pull-up resistor. What's that time constant? Tau pull-up is 20 times 10 to the minus 12 times 10 to the 5th, which is 2 microseconds, right? So, if I just eliminated this, set these port pins to pull on the pull-up, when I read the key one cycle later, I would be right here on the charging curve. And I want to be up here because the code assumes that the pull-ups are turned on and the outputs are high, or the inputs are high. Inputs are high before the button is checked. And so what was happening is that when I read this without the delay, I made a very awesome random number generator because all of the inputs were still floating at some random value. And I strongly suggest that you take this demo code and you decrease this time to 2 microseconds, see what happens, to 1 microsecond, see what happens. It fails someplace lower than 5. But it depends on how long your wires are and how close your body is to the keypad, because depending on your surface area, you're about 100 picofarad capacitor. So even though with output active, the time constants are trivial. With the output inactive, but the pull-up turned on, the time constants are on the order of 30 or 40 cycles. And so you have to delay for some amount of time.
How often does this burn you on, like, breadboards that you're gonna, when you go to build it on an actual PCB?
How often does it burn you? Just often enough that you wish it didn't. I mean, it almost always works. Well, the nice thing about going from a whiteboard to a PC is that the parasitic capacitances on a whiteboard are usually much greater than on a PC. So everything gets better on the PC. Every once in a while, though, that doesn't work because you might put a nice ground plane to keep noise down and double the capacitance. Anybody have any experience with this? Things they wish hadn't happened? Pavel, yeah, you've seen that? Yeah. I've seen it. Not too often. Makes you obsessive, though, about this stuff. Okay, so the very next thing we're going to do after this, then, is to... Any questions on this before I erase it? Right, so pull up, turned on. Pull up is turned on here. Here, port is switched. Here, port is switched from output low to input. Two erasers. All right, so now we're going to set DDRD to read the other direction, so it's 0xF0. And port D goes to 0x0F. We delay microseconds 5, and then read key again. Well, we're gonna OR key the old value of key, which is the upper 4 bits, with the lower 4 bits, and we're guaranteed for that OR to work because the output bits are always low. So the only bits that can possibly be high are the input bits. Questions? Okay, at this point now we have a scan code. If no button is pushed, it's going to be FF. If more than one button is pushed, there's going to be more than 1 0 in at least one of the nibbles. And otherwise, the value is going to fall into this 16-entry table up here. So we have to slide through the table and check for all of the values. I'm not going to do that right now because it's just slightly longer than I have left. So, we got 7 minutes. Any questions about Lab 2?
Yeah, to measure the frequencies, we will use the timer 1 input input capture register, but it's not necessary to use the ISR to calculate the difference.
It is necessary to use the ISR. Because how do you know when a new capture is ready if you don't use the ISR?
Because you mentioned like we can do 5 measurements each second, so I would do, I'm considering whether just do a scheduled job, like a scheduled task running every 200 milliseconds.
So 200 milliseconds goes by, you read the capture register.
Yes.
It tells you nothing
Well,
because you don't know when the last time it was read.
I will have another like variable stored the last time, like.
So 200 milliseconds before you read it, now you read it 200 milliseconds later. How many times has it overflowed? I don't know.
Okay, yeah.
You have to use an interrupt-driven system to get to know when the capture actually occurred. How are you going to detect overflow?
Overflow interrupt.
So you could set 2 interrupts. You could set the capture interrupt on timer 1 and the overflow interrupt. If the capture interrupt occurs, then you know you got a capture. If the overflow interrupt occurs, now you know that the period of the square wave coming in is too long to measure with the current prescaler, and you have to modify the prescaler. Any other questions? Let's talk about final projects. The week before spring break, you have to hand in a 2-page summary of what you're going to do for a final project. So that's now less than a month away. And so you better start thinking. Over spring break, see, the TAs don't get spring break off. TAs are employees of the university and don't get spring break off. They have to work through spring break, just like me. And like you. And so their job over spring break is to score your final project proposals, not necessarily for grade, but for doability, for possibility of actual construction. Is this crazy hard? Is it so easy that it's too easy? Is it 3-person work or 2 persons worth of work? What are the reasonable sub-goals that you can break the system down into so that so you always have something ready to demo? So we're going to ask for two pages nominal of information about what you're going to do. What week is that? That's like March 6th or 8th or something like that, or 10th or 11th, or I think it's spring break is the 3rd week in March this year, isn't it? So it'll be the 2nd week in March. That's about a month from now. It is not too early to start thinking about this, because that lab period, you have a homework due, a lab due, and a homework due. 2 homeworks plus a lab. Don't wait till the last minute.
I just have a quick question about the lab. For resistance auto ranging, is it necessary to auto range both the ref and the resistor you're using, or just auto range?
So for measuring resistance, do you need to auto range VREF and the resistor, or just the resistor? I think it is sufficient to auto range the resistor.
Okay, just set the ref to 5.
Yeah, set VREF to whatever you feel like and auto range the resistor, yes. Because it's all ratio measurements anyway with the resistor. So VREF actually doesn't matter. So set it to 5.
Do you want
Weekly
weekly reports during the
reports during the final project, it is up to the TA. Some TAs want a written report every week. Some TAs would like a 1-paragraph email the night before your section. Some TAs want verbal 5-minute summary in section. You have to be there every week for your section. You have to report every week on what you've done. But the format is the option of the TA. is negotiable with the TA. But yes, there will be a weekly report necessary, weekly progress report necessary. Otherwise, 5 weeks is a long time. Those first 2 weeks just fly by and nothing happens. And then another week goes by and you say, uh-oh. Don't get yourself in that situation. And remember, there is a bonus for finishing early. If you finish 30 days early, it's worth 15 points. If you finish the first day of the first lab of the final project, it's a 15-point bonus. That's a half of the class score. That's a 7.5-point bonus on the final grade. That's a significant bonus. Get started early, folks. Don't wait till the last minute. And Friday section, that monster Friday section of 30 people, you know how long it's going to take us to get through 15 projects? Till way after the end of slope day. So, demo early. If you feel like going to slope day, I don't care. I'll be here. It's too hard on the kidneys and liver. Okay,